Today in class, you'll be completing two lab notebook pages, lab notebook page 95 and lab notebook page 97. Feel free to pause the video at any time. You'll be starting with response sheet reaction. Grandmother ate too many chili peppers for supper. She moaned. I need an antacid tablet. Beth found the package of antacid tablets and read the label. The active ingredient was calcium carbonate. Beth said, "This will give you some relief." Number 1. Explain why Beth thought the antacid tablet would help grandmother. Use complete sentences and correct punctuation and grammar to answer this question. Number 2. Use chemical formulas to write the equation for the reaction. Note, here are the formulas for some of the substances you have used. CO2, carbon dioxide. CaCO3, calcium carbonate. CaCl2, calcium chloride. CaOH2, calcium hydroxide. H2O, water. HCl, hydrochloric acid. MgSO4, magnesium sulfate. NaHCO3, sodium bicarbonate. Na2CO3, sodium carbonate. And NaCl, table salt. Feel free to use any classroom resources to answer these two questions. You can look back at Investigation 9, Part 1 and 2, pages 88 through 91 to help you answer that question. And you can use the chemical formulas as well. Use all the time you need to answer that question to the best of your ability. Pause the video while you work. When you're finished, you can hit play. I'm sure you did a great job at answering those two questions to the best of your ability. Welcome back. The next section will be to work on page 97, the Lavoisier questions. Number 1. Why did the mercuric oxide in Lavoisier's reaction chamber weigh more than the mercury metal? Number 2. Why was there less air in Lavoisier's reaction chamber after he heated the mercury for 12 days? Number 3. What are some of the reasons Lavoisier is considered to be the father of modern chemistry? The reading to answer these questions starts on page 69 in your textbook. Antoine Laurent Lavoisier, the father of modern chemistry. Antoine Laurent Lavoisier, the father of modern chemistry. In 1794, during the French Revolution, a man was executed. This man was a famous chemist who helped revolutionize the study of chemistry. His experiments changed the way chemists understood fire. His work stressed the importance of careful measurement and experiments. He created a new language of chemistry and defended the idea that matter is not lost or gained during chemical reactions. Why was Antoine Laurent Lavoisier's head cut off? Was it because of these ideas? Perhaps looking at his life and his work will help us understand. Lavoisier was born when King Louis XV ruled France. Because his family was wealthy, young Lavoisier was able to get an education. As a young man, he practiced law and owned a tax-collecting agency. Lavoisier was a prominent citizen in his community. But it is Lavoisier's second life as a scientist for which he is remembered. Early in the morning and late at night, he studied mathematics, geology, physics, biology, and chemistry. His work in geology was so impressive that he was elected for the French Academy of Sciences when he was 25 years old. Debunking phlogiston. Lavoisier's interest in science turned more and more toward chemistry. One of many things he studied was combustion, the chemical reaction we usually call burning. During the 1600s and 1700s, chemists thought that all flammable substances contained an odorless, colorless substance called phlogiston. It was generally thought that when a substance burned, it gave up this phlogiston. and the material left behind weighed less than it did before. Lavoisier thought the theory of phlogiston was nonsense. He called it a fatal error to chemistry. He set out to disprove this phlogiston theory. In 1772, Lavoisier performed a series of experiments based on the work of another French chemist, Louis Bernard Guétin de Morveau. He kept very detailed records, carefully measuring the weights of the materials before and after he burned them. His results showed that substances such as sulfur and phosphorus actually gained weight when burned. In 1774, Lavoisier met the English chemist Joseph Priestley. Priestley told him that he had discovered a new kind of air by burning mercuric oxide. Priestley tested animals in a closed container with this new air and found that they lived longer than animals in closed containers with regular air. Intrigued, Lavoisier repeated Priestley's mercuric oxide experiments, but unlike Priestley, he very systematically weighed and measured all parts of his experiments. He collected the gas given off and found that a candle thrust into the gas burned brighter than he could have imagined. Could Priestley's new air somehow be involved in the burning of other substances? Could it also explain why the substances he had burned before gained weight? To find answers to his questions, Lavoisier devised a new piece of equipment. It was a kind of carefully handcrafted, airtight reaction chamber and oven. He put liquid mercury into the reaction chamber, put the chamber in the oven, and heated it for 12 days. Piston, air, liquid mercury, heat. 3 interesting things happened. The mercury turned into a reddish solid substance. The volume of the air in the container decreased from 50 to 42 cubic inches, and the new solid substance weighed more than the mercury. Piston, air reduced volume, solid mercuric oxide. Lavoisier concluded that the missing 8 cubic inches of air had combined with the shiny liquid mercury to produce the dull red mercuric oxide. The additional weight of the mercuric oxide was exactly equal to the weight of the missing 8 cubic inches of air. He then heated the solid mercuric oxide to a higher temperature. It turned back into liquid mercury and gave off the exact amount of gas that had been lost before. This change was proof to Lavoisier that combustion does not burn phlogiston out of a substance, but rather combines the substance with a part of the air surrounding the substance. In 1785, he said that his ideas should replace the idea of phlogiston. Lavoisier later named this ingredient in air oxygen, a name that we still use. Some important chemists, including Priestley, who first isolated oxygen and called it new air, disagreed with Lavoisier's conclusion. They remained solid supporters of the phlogiston theory, but in the end, the precisely measured results of Lavoisier's experiments convinced the new generation of chemists that oxygen explained combustion. Other major contributions. What impressed Lavoisier's supporters more than anything else was his careful attention to quantitative detail. He spent a lot of his own money designing and building instruments, including balances as precise as those used today. With these instruments, he was able to establish the law of conservation of mass, which states that matter is neither gained nor lost during a chemical reaction. Lavoisier was also quite the showman, making sure that his equipment was not only precise but flashy. One piece he developed, the gasometer, was used to measure volumes of gas. It stood about 6 feet tall, was made of gleaming brass, and was one of the most expensive pieces of chemistry apparatus anyone has ever seen. It cost more than $250,000 in today's dollars. Although its results were no better than anyone else's, its sheer expense and beauty made people begin to think of chemistry as serious science. Chemistry, a serious science? Many people at the time still thought of chemistry as magic, but Lavoisier's chemical revolution was changing that. In addition to his experiments, he developed the system of chemical names that still exists today. This new vocabulary enabled chemists to communicate effectively and establish chemistry as an independent, respected science. To top it all off, he wrote what is now considered to be the first textbook of chemistry, The Elements of Chemistry, in 1789. In it, he introduced the idea of elements, substances that could not be broken down into simpler substances. He included heat and light as substances, though they are now known to be energy. Lavoisier was wrong about one major idea. When presented with the idea of atoms, tiny, unchangeable, defining units of an element, he dismissed them as impossible. Death at such a young age. Were these new ideas threatening to establish scientific thought? Did Lavoisier deserve to lose his head for his ideas about chemistry? Actually, no. Science had been experiencing a revolution in thought called the Enlightenment. The intellectual world was ready to accept arguments based on experimentation and logical thought. Lavoisier and the chemists of the chemical revolution used those techniques. But it all came tumbling down for Lavoisier when the French Revolution broke out in 1789, the same year he published The Elements of Chemistry. The French peasants had had enough of the monarchy and class system, and they rebelled against the king. The targets of their fury included anyone associated with the government. Lavoisier was a tax collector, and for that he was arrested, convicted of crimes against the people of France, and beheaded. Review questions. Why did mercuric oxide in Lavoisier's reaction chamber weigh more than the mercury metal? 2. Why was there less air in Lavoisier's reaction chamber after he heated the mercury for 12 days? 3. What are some of the reasons Lavoisier is considered to be the father of modern chemistry? You now have silent work time to answer those 3 questions on page 97 in your lab notebook. You can either answer this on your lab packet paper copy or going to Shobi Investigation 9.